when we look to 9.5 here, we're going to take a look at some ideas that really fit most naturally into a statistics course, but as with all math, there's always crossover between some of these ideas. And so we're going to take a look at some issues that relate to, that we're essentially going to need for the ideas of probability. But what we're looking at to begin with is the number of arrangements, the number of choices that can occur. They're all kind of synonyms for the same type of problems. But so we're going to first think about how many ways, how many outcomes could there be in a certain situation. So the first idea here is called the addition principle, and it's just simply saying how many entrees are there as long as there's no overlap. Like, so what we're looking at is there's two veggie options, there's five meat options. As long as there's no option that is in both categories, there's no overlap, so no veggie meat category that, or veggie meat plate that's been counted twice. All we have to do is just add them up. It's just as intuitive as that. So again, as long as there's no overlap, something that's in both categories, if we want to know how many options we have as we look at the menu, all we have to do is add them. So we have two veggie options, five meat options. We obviously have seven options. We can just simply add. All right, so if we walk into a computer store and we've got three desktop computers, four laptop computers, and we simply want to know how many computer options are there, well, there's clearly no overlap here. There's no such thing as a laptop desktop. So these are distinct categories. All we have to do is add them, and so we would get seven. Okay, now here is a really important idea. Um, I, I don't know if I should break down this whole thing. Um, Here's how I would do it in statistics. Let me just give you the quick version of it. So if we have a number of possible choices in one category and another possible number of choices in a second, if we wanted to know the total number of ways we could arrange these, in other words, how many, so in this illustration, it's how many skirts and blouses, how many different ways could they match up? Well, it's a super important idea that turns out all it has to be is how many possibilities are there for the first choice, how many possibilities are for the second, and all you have to do is multiply them. So suppose I had two choices, red or blue, for the color of a shirt, and then I had number one, number two, number three. So in the second choice. So I've got the color of the shirt and I've got the style. There's three choices. So what we've said here is that there's two colors and three styles. Well, look at the number of possible outcomes we've created. We've created red and one, red and two, red and three, blue and one, blue and two, blue and three. Well, we had 1, 2, 3, 4, 5, 6 possible total choices. We've created 6 of these tree diagrams, 6 stems. Now, all it took, though, all we really did was multiply the number of choices for the color and the number of styles, and it turned out to be 6. So you could manually work your way down these trees and find red goes with each of these, blue goes with each of these. But what turns out to happen is you simply need to know the number of choices for each option, and you can multiply the choices together to find the total different ways that you could have arranged them. So in this story here, we have two skirts, we've got two blouses, we've got two sweaters. Okay, well, instead of making the tree and like saying, okay, how many different ways could this happen? All you have to do is multiply. 2 times 4 times 2. There's 16 possible ways you could arrange these clothes. So when we get to this one, we've got a restaurant here. We've got 3 types of breakfast sandwiches. We've got 4 side dishes and 5 beverage choices. So if we want to know all the different ways you could make a different breakfast, well, all we have to do is multiply these. These are 20 times 3. We've got 60. Okay, now when we saw factorial earlier in the book, we talked about the idea of a factorial, and its actual basis here is in the idea of a permutation. And so here's the idea of a permutation. Let's see. Okay, so we've got swimmers at a competition, and we want to see how many ways they can finish in the race. So we want to know first, second, and third place. Okay, well, isn't it possible that 9 people could get first place, right? You could say 9 of those swimmers all have a chance to get first place. But now, if there are 9 people who have a chance at first place, somebody won, right? So I don't know who of the 9 won, but one of them won. So if I'm looking to second place, it's now 8 people are left. And if I move to third place, well, somebody won and somebody got second. Now there's only 7 possible people left who could have gotten third. Now we're actually building our way here to a permutation. So we've got 9 times 8 times 7. So there'd be 504 ways. So 9 people could get first, but one person's gotten first. There's only 8 people left. Well, someone's gotten first, somebody's gotten second. There's only 7 people left who could have gotten third. If we say, here's the number of choices we have for first place, here's the choices for second, here's the choices for third, we said we can just multiply those choices together, and we have 504. Okay. Yeah, I don't think I would introduce it quite like this, but so here's the idea. What they're saying is Ariel's going to get first place. Now, what are the other possibilities? So this girl's so good, she's guaranteed to win. Well, if we're looking at first place, there's only one person who's going to get that. It's going to be Ariel. Now, let's go to second place. Well, there's only 8 swimmers left. One person has already taken up first place. We're still back down to 8. And now, since first and second are now filled, there's only 7 people left for third. So we multiply our choices. First times second times third. One person's got it. There's only one chance at first. There's 8 chances at second, 7 chances at third. Multiply those together. That's our total number of arrangements. There are 56 ways that Ariel can get first place. Okay, now they're saying they're lining everybody up for a photo. Now this is typically the way that I should have started with this one. So this is the same idea. We're going to put people in line for this photograph. 9 people could be standing on the far left of this photograph. But after someone is standing in that spot, so the next spot only has 8 possibilities left. And then 7, and then 6, and then 5, so on. As we go down, we keep using up one of the swimmers. Somebody stood in the line already. And so this is the idea of a permutation. It's 9 factorial. It's 9 times 8 times 7 times 6 times 5 times 4, all the way down. And we get 9 factorial, which if you punch it on your calculator, get 362,880. But it's the same thing. You could do it by hand if you wanted. And the idea is simply we're arranging the people, and the order that they're standing in line is important. We have somebody standing here. Well, someone's been used up. That leaves us only 8, then 7, then 6, right on down the line. Okay, so we've got a family of 5. Let's see. Okay, so the family is lining up for a portrait. So the same idea. We've got our 5 spots here. Now, how many possible people could be the first person in line? Well, 5 of them could be, right? So these are all going to be multiplied. We've got 5 of them. But somebody's standing there. You can't have that not the case. Someone has been standing here, so we've only got 4 people left for the second spot in line. Somebody's standing there, so there's only in these first 2 spots, there's only 3 people left for the next spot. There's only 2 people left. There's only 1. So in other words, this is the same thing as 5 factorial. We could just multiply down the line. And what's 5 factorial? It turns out to be 120. Okay. Okay, so the family member is only, or the photographer is only taking pictures with 3 people at a time, if I'm understanding this right. So what could happen? Well, there's 5 family members that could be standing there, but somebody's standing there, leaves us 4, and then 3. So we've got 20, we've got 60. So he stopped. After 3 spots, the other 2 people are not in the photograph. Okay, so the parents are required to stand on each end. So here's what we've got. Okay, so how many possible parents could be standing here on the left side? Well, there's 2. Maybe it's mom, maybe it's dad. So we got 2 possibilities there. Okay, well, somebody is standing there. That leaves 3 possible choices. So there's the only thing, kids have to stand in the middle. So mom or dad might be here, but there are 3 kids left to stand in this spot. There are 2 kids left to stand in this spot. There's 1 kid left for there. Now, mom or dad is on this side. Well, that leaves mom or dad. There's only one other person who could be here. Does that make sense? So again, parents have to be on the outside. So there's two possibilities. Maybe it's mom or dad on the far left. Now, when we move to the middle, it's the kids. There are 3 kids. Then there's only 2 kids left. Then there's only 1. Well, why is this 1 on this side? Well, because we had a parent stand on the left. There's only one possible parent who could be standing on the right. So we get 6, we get 12, and that's our arrangements. All right, now we're going to take a look at a fancy formula for the permutations of indistinct objects, but it's really not as impressive as it looks like. So let me take you through. So here's our formula. What it means is that we've got n people, and we're taking them, some number of them together at the same time. So like permutation, we've got 5 people in the family. We're taking 3 at a time for the photographs. So the way the formula works is we're going to do 5 factorial over 5 minus 3 factorial. And you say, well, what does this craziness mean? 5 factorial over 2 factorial. What is this? It's nothing at all. So here's what this would be. 5 times 4 times 3 times 2 times 1. That's what the top is, right? If we had 5 family members, we could just line them all up. That's the way it works, 5 factorial. But we're not lining up everybody. We're taking only 3 people at a time. And so we don't need these last 2 spots. Do you see what I'm saying? We're taking 5 people, but we have 5, but we're taking only 3 at a time. So 5, 4, 3, 2, 1 would be as if everybody just lined up. That's the number of choices. But we're stopping after we get to 3. 5, 4, 3. We're going to stop right here, and the last 2 people are not going to get counted. Well, look what the bottom does here. 5 minus 3 factorial is 2 factorial, or 2 times 1. So what we're doing, what this formula is doing is it's simply cutting off the people that are not getting chosen. That's it. That's all this is. It's a fancy way of saying 5 people taken 3 at a time. After we get down to the 3 people, we're just going to stop. We're going to divide away the people that aren't getting used. Do you see what I'm saying? So 5, 4, 3, 2, 1 would be the 5 people being arranged. But we're stopping after 3. So this bottom is, okay, where are you stopping? You're stopping out of 3, which means we don't need these 2. And we're dividing them away from if they're the same on the top and the bottom, we could just get rid of them. So in other words, this fancy formula is simply saying we're just stopping after the people that we don't need. Now, I hope that makes sense. You can memorize it if you want, but it's really not intended to be like that. It's a math formula that looks complicated, but it's really quite simple. So here we've got 9 questions, and we're taking them, or 12 questions, taken 9 at a time. How many different ways could we make this possible test? Well, what we're doing is there's 12 questions, so 12 factorial. Maybe there's 12 choices for the first question, 11 questions for the next, 10 for the next, 9 for the next, 8. So this is actually 12 factorial. We could go all the way down. But what we're going to do is we're going to stop after we've selected 9 questions. That's what this bottom is doing. So it's just getting rid of after 9, we're getting rid of these last choices. That's what it's doing. All we're doing is chopping off these last choices. Okay, now if you're not following me here, you can always just plug and chug, but it really does help to understand this better. So we've got 12 factorial, 12 minus 9. 12 taken 9 at a time leaves us 3 factorial. You can divide those, and that's where we get our possible arrangements for this test, possible permutations. Okay, so a play has taken 7 actors, and they're all lining up. So you could think of it like this: 7 taken 7 at a time. How do they do that notation? Yeah, 7 taken 7 at a time. You could think of it like this. And so it's not really necessary, but so what we do next is 7 minus 7 factorial. So this is the fancy way. 7 factorial is going to be over 0 factorial. We learned earlier that 0 factorial is just 1. So this is 7 factorial divided by 1. But let's just think of it like we got 7 people on the stage. Well, there's 7 actors who could stand in the first spot. That leaves 6 for the next, 5 for the next, 4 for the next, 3, 2, 1. And everybody's standing on the stage, so we used up everyone. That's the same as 7 factorial. So I don't know what 7 factorial, there it is. If I crunch 7 factorial on my calculator, it's 5,040. Again, if you need, I believe factorial, let me just check real quick. I believe factorial is just under math. No, it isn't. No, if you hit math and then go to probability, that's where you'll find. So math, and then over to the right to the top says probability. That's where you'll find factorial. Okay, let's see. All right, so permutation again here, but we're taking 5 at a time. Okay. So we've got 7 factorial divided by 7 minus 5 factorial. Okay, so that's 7 factorial divided by 2 factorial. Now that's the formula, but what's really happening here is 7 times 6 times 5 times 4 times 3. We're taking 1, 2, 3, 4, 5 people. These are saying exactly the same thing. It's stopping here after 3, and this is doing the same thing. It's stopping here once we get here. Same exact thing. These are saying the same thing. Now, if we crunch those, we get 2,520. Same thing. You could do 7 factorial divided by 2 factorial, or you could just do 7 times 6 times 5 times 4 times 3. You'd get the same thing. All right, now we're going to move to something called combinations. And combinations are this idea. Yeah, let me think of it. The difference between the two, a permutation is the order matters. Okay, so a permutation, the order matters. A combination, order doesn't matter. Okay, so what does that mean? All right, so if we're lining everybody up for a family photo and we've got 5 people, it matters. Whoever is first matters. It is not the same order if Beth is first and Beth is last. That is not the same order. So it is unique depending on where you're standing in this line. That's a permutation. The order matters. Where you are is different. But suppose I was saying I want to select 3 people from our class to go on a field trip. Well, okay, I take Beth, I take Mike, and I take, I don't know, Tim. If I were to have also picked Tim, Beth, and Mike in a different order, that's the same people. That didn't do anything differently. And so what I'm saying here is sometimes a permutation has a unique order. Everybody is in a very unique place. It matters if you're standing on the far left or the far right or wherever you are in the line. That matters. But with a combination, it doesn't matter at all. I've just simply selected 3 people, so there are different ways that could have happened, but that hasn't changed anything. And so if you look at this formula here, n factorial over n minus r factorial, we already saw that's a permutation. How many people do you have? When are you stopping? So if you're only taking 3 of them at a time, this was a permutation. Now, what's this extra r factorial on here for? Well, there are different ways to arrange 3 people. All the ways, so if you have Beth, Mike, and Tim, there are 3 factorial ways you could arrange them. It could be Beth, then that leaves the other 2, then the other 1. So how many ways can you arrange 3 people? It's 3 factorial. Well, what this formula is doing is saying, hey, we have some repeats. Combination, I don't care who's first, I don't care who's second, I don't care who's third. I just want to know all the groups where the people get picked. So we're going to divide away the repeats. We have some repeats. Beth, Mike, and Tim is the same as Tim, Beth, and Mike. And there's one other option here, or there's several other options here. The repeated arrangements don't mean anything to me, so I'm going to divide them away. So if I'm taking groups of 3, I'm going to divide by 3 factorial because I don't care at the order. If they got picked, they got picked. I don't care if they're first, second, or third, or whatever. Okay, so let's take a look at this. Okay, so we have a combination here. I don't care hold on. Yeah, let me go back for a second. And here's a little trick I do for permutations and combinations. A way to tell the difference, if just logically it doesn't make sense to you whether there's an order, here's what I teach people. Permutations have some kind of prefix. Combinations have none. And so what I mean is this. If I'm selecting people for a position on the council, and somebody's going to be president, somebody's going to be secretary, somebody's going to be treasurer, there is some prefix. There is some name, or if they're running a race, first, second, third, a batting order, the first place, the second place, the third, there's some prefix to it. On a football team, the left guard, the center, there's some name title to each of the spots. Well, then the position you're in matters. It isn't the same whether you're the president or the treasurer, so the order matters, and you'll have some kind of prefix. But a combination, there isn't anything. It's just like, okay, there's just a bunch of people being chosen. They're all in a pile. There was no prefix, no titles to the spots. That's a combination, and the order doesn't matter. So we're at a restaurant, and they have 5 side dish options, and we can pick 2. Okay, well, if I've got corn and mashed potatoes, it doesn't matter if one's on the... We don't care. There's no prefix to it. There's no place in line. It's just that I've picked them. They're on my plate. That's good enough. So the order here doesn't matter. So I'm doing a combination of 5 taken 2 at a time. So the top here is how many things have how many possibilities are there? There's 5 options. The 5 minus 2 is just saying we're stopping after we take two choices. That's what we did. This is exactly the same as the permutation formula. Then we're dividing away the fact for all the arrangements of 2 sides. So mashed potatoes and corn is the same as corn and mashed potatoes. We have a repeat, so we're dividing it away. 2 factorial is dividing away those repeats. Okay, now the second one is saying, okay, well, it's 5 taken 3 at a time, but we don't care about the order. You got these things on your plate, mashed potatoes, corn, whatever, bread, whatever your other, cornbread, I don't know. It doesn't matter the order. They're just on your plate. So this is a combination, but now it's 5 factorial. We're taking 3 at a time. We're cutting away the repeats. All the ways you could arrange the 3 things are repeated because we don't care. It doesn't matter. There's our formula. 5 factorial divided by 3 factorial divided by 2 factorial. Okay. All right, so we've got ice cream flavors. We've got 10 taken 3 at a time. Now, they're not saying the order matters here. There's no prefix. It's not the first ice cream flavor, the second. There's not a title, president, vice president. It's just a bunch of ice cream flavors on a banana split. That's all it is. So it's 10 taken 3 at a time. So we've got 10 factorial over 10 minus 3 factorial, and then we don't care how many ways you arrange the 3 flavors. It doesn't matter if they repeat, so we're dividing away any repeats. So we have 10 factorial divided by 3 factorial times 7 factorial. Now these are big numbers here. You could do it by hand and kind of simplify this by, I guess I'll show you. So 10. So the 7 factorial is going to cut away everything from 7 on down. So here's what the top really is, and then the bottom is really this. So, but you can just do it on your calculator if you don't understand. 10 times 9 times 8 divided by 3 times 2 times 1 is what we're going to really wind up getting. But you can do it this either way. These are the same thing. I'm just showing you a shortcut. Crunch this on your calculator. You're going to get 120. So the order does not matter. Okay, I had to pause on this. This is a question I hadn't seen or thought through very much. Couldn't remember what this was about. So we have a formula here that says how many different subsets can we create? But here's really the idea. We've got 1, 2, 3, 4 choices to put on our baked potato. What we're going to do though is we're going to think of it like this. Are we putting butter on? Yes or no? So when it comes to butter, there's 2 possibilities, yes or no. Are we putting butter on, right? So for butter, there's 2 choices. For cheese, yes or no, there's two choices. For sour cream, there's two choices. And I missed one. Chives, there's two choices. It's either yes or no. So another way to think of this, how many different subsets could there be for topping a baked potato? What we're really doing here is just simply asking the question each time. There are two choices for each one. So it's 2 times 2 times 2 times 2, right? Well, it's yes or no, yes or no, yes or no, yes or no. Okay. Well, isn't 2 times 2 times 2 times 2 the same as 2 to the fourth? There were 4 options. It was 2 to the fourth power. So basically what we're saying here is how many different subsets could we make out of our choices? We're simply asking for each of them, yes or no, are they included? Yes or no, are they included? And so we simply have this formula, 2 to the n. 2 times how many different choices or options we had. So let's see if we've got another one here. So we've got 6 toppings to choose from. How many different sundaes could you do? You could think of it as if each topping is either on the ice cream or it's not. Yes or no. So another way to create this same kind of idea is 2 to the 6th. 2 choices for the first topping, 2 choices for the second, 2. So yes or no, 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 yes or no. Well, that's 2 to the 6th. 2 to the 6 options. So 64. Okay, let's see. All right. So permutations of non-distinct objects. Here's what it means. That if I were, I'm trying to think. I don't want to use the one that I know is on the worksheets that I use sometimes. Well, I'm going to start with this one. I can't think of anything easier. So here's what we're going to do. We're going to arrange the letters in this word distinct. Now, how many letters do we have? 1, 2, 3, 4, 5, 6, 7, 8. We have 8 letters. Okay, well, doesn't that mean 8 factorial? Or the way that I could rearrange these letters? But here's the problem. Some of the letters are repeat. They're not unique. So if I build a letter here, so let's just stay with this word distinct. If I had arranged it so this T number 1 and this T number 2 were interchanged, then that creates the same word. But when I arrange them, I create it as if distinct with the T here is the same as distinct with number 2 here and number 1 there. Do you see what I'm saying? If you flip those T's, it's still the same word. We haven't created a unique word. So we have repeats that don't change anything. They haven't created something unique. And so whenever I have a repeat, I'm going to divide away the possibilities. There were 2 T's. Well, that means 2 factorial ways to arrange the T's, but they're repeats. So I'm going to divide those repeats away. Now, the letter I's. There's also 2 I's, and they repeat. So there are 2 factorial ways to arrange the letter I. And they're repeats. They're not creating unique words because they're interchangeable. So I would divide them away. So in other words, what this formula is saying is, okay, well, how many options do you have? That's n factorial. But if you have any repeats, 2 things that are not distinct, that are not creating unique permutations, then you just divide them away with a factorial. So we have 8 factorial. There are 8 letters. But T and I both repeat. So 2 factorial, 2 factorial, we're going to divide that away. And I get 10,080 permutations. Okay, so let's try it again with the word carrier here. I've got 1, 2, 3, 4, 5, 6, 7. I've got 7 factorial letters, but we've got repeats. The letter R repeats 1, 2, 3 times. So 3 factorial is going to be all the ways you could rearrange those 3 R's. You can just rearrange them in three factorial ways, but we don't need them. They're repeats, so we divide by 3 factorial. Now, do we have any other repeats? No, just the R's repeat, so that would be my formula. So 7 factorial divided by 3 factorial is going to get me 840. Okay, that's a pretty quick crash course on combinations and permutations. I hope that made some sense, and hopefully that'll get you started.